Okay, so first and foremost, what I want to do is I want to talk to you about a software which is called the Lotus Engine Simulation. This software would allow you to simulate single cylinder and multi-cylinder engines. And why is this important? This is important because once we get some design specs, based on the design specs, we can come up with some approximate dimensions for the cylinder size, bore, stroke, and other engine parameters. But as we start doing the detailed calculations, the engine design is an intense process. It requires knowledge not only of mechanical components, but thermodynamic processes, computational fluid dynamics, fluid structure interaction, and then you need to understand how the dynamics propagates. For example, if you have a fluid flow, if it goes through different pipes, there will be some resistance to the fluid flow that affects the performance of the engine. So all these things we cannot do by hand. So for that, we have to use the software. So in today's class, what I would do is I will introduce you to the software. The free version of the software is can be downloaded on Lotus Engine Simulation website. I will walk you through the important parts of the software, and it's actually very nice. So you have blocks, you drag and drop blocks into the canvas, make the appropriate connections, enter the properties for those blocks, and it will run the internal simulation. It will have its own solvers, and it will give you the predicted performance of an engine. It will also show you the losses at different stages of engine. So that would be very, very useful when you want to design or when you go to industry. So what I'm going to do is I'm going to share my screen. So, and I want you to go to Lotus Engine Simulation. I don't know, Lotus Car is a company of European cars. They design and build fantastic high performance cars. So I want you to go through this Lotus engineering software. And then they have free versions of the software and the paid versions of software. We won't have time to discuss the suspension design. We won't have time to discuss the valve train design. But please understand, as I talk about the valve design, valve train design, there is a software that you can use to design the valve profiles. You can actually attach the springs, you can attach the cam profiles, you can design the follower profiles to make sure the appropriate opening and close timings of the valves are achieved. And this is very important if you are driving a Honda engine, IV-Tech engine. They have two different valve profiles. One valve profile is open and closing the valve at low speed, and another profile is opening and closing the valve at high speeds. And that is needed because you don't have enough time for the charge to enter the combustion chamber when the engine is running at high speed. So you need to open the valves for longer duration of time. If you use this software, you can actually predict the valve timing diagrams. You can actually create the valve shapes. So basically, and then the cam shapes. So basically, all these design softwares are super duper useful when you try to design an engine. If you want to go into design of suspensions, for example, if you're part of SAE Mini Baha team, which is at Poly campus, which is again, one team is at Tempe campus. And if you want to design the suspension parts, then you can use this suspension software. These softwares you can actually get free if you are a student, but then you will have to send them an email, provide your information, and they will send it to you. But one thing is I want you to talk about is there is one software that we will use in the class, which is Lotus Engine Simulation freeware. So unfortunately, this software only runs on Windows. So please download this software and install it on your machine. And once this software is installed, I will show you what will happen. There is also fantastic help file which getting started using Lotus Engine Simulation that actually walks you. There are tutorials, and what I'm going to do is I'm going to show you this. And I didn't ask this as part of the course because I know you guys are super busy with a compressed schedule and a lot of assignments, but there are some tutorials I would strongly recommend you to do that will really give you an in-depth analysis and the feel for engine design. So for an example, if you apply for jobs at General Motors, Ford, or MTD, which is right here, or if you decide to work for some engine design or a firm or engine development firm or major automotive manufacturers, something like this would be super duper useful. So this tutorial or this manual is available online for download. Now I want to show you, I'll walk you through the software. So it's not like, so first chapter of this manual is introducing the Lotus engine simulation. I will give you a brief overview. I will actually walk you through one simple simulation. But the second chapter is actually an important chapter. It's a basic single cylinder engine design. So if you have an engine and it's very difficult to predict the performance of engine because engine is such a complex mechanism, complex system that involves thermodynamics, chemistry, then mechanical system, electrical system, electrons, all that stuff. So what you do is you go through these step-by-step processes. An engine can use different type of fuels. It can use different grades of fuels. So manually, it's not possible to go through all those iterations. But what you do is you follow this process. Again, depending upon whether the engine is new or engine is old, the engine capacity or the frictional losses could be different. So you need to account for all those variations. So this chapter kind of walks you through a very simple engine design process, step by step. It also talks about how to design engines that can operate in multi-fuel situation. So for an example, if you are designing a stationary engine, but you are not so sure about the quality of fuel, and many a times you don't know what type of fuel quality you are using, but you want to still make sure that your engine is able to perform and meet the performance requirements. It's able to produce power. It shouldn't stall. It shouldn't knock. It shouldn't explode. So all those trial and errors, different design of experiments can be actually done within this environment for single cylinder engine. Engine is not an isolated system. So what you need is you need a fuel tank, you need a fuel pump, you need to regulate the pressure, you need to maintain the inlet pressure, all that stuff. So if you want to include the effects of piping, effects of fuel delivery, effect of different types of mufflers, effect of different types of sound suppression systems, single exhaust, multi-exhaust, deflected exhaust, all those stuff, they matter. They affect the performance of engine. So you can actually add those pipe models that will tell you if you actually bend this exhaust in this particular angle, what would happen to engine performance? If you actually split the exhaust what would happen to the engine power and all those stuff. So then what you do is, so that's for that. You have this second chapter 3, which is with intake pipes. Then what you do is you can actually do some type of optimization, because some of these requirements could be conflicting. So you have to see what is the trade-off, what is the best configuration that you want to focus on. So for that, you have these parametric studies. And this is where you actually design multi-cylinder engines, not just a single cylinder engine, but 2 or more engines working together. And then what you have is you have some concept tool. I don't think we have access to the advanced functionalities of softwares, but the basic functionality is good just to get some familiarity with the software. And when you go to industry, if you are familiar with Lotus engine simulation, that would be a stepping stone. Because if you go to industry, you would be using more advanced software like Ricardo engine simulation, and GM and Ford, they have their own softwares and own databases. You'll be working with those, but the underlying principles are the same. There are different combustion models, there are different CFD models, there are different friction models. And so all those you have to be familiar. So if you want to, if you have a, so this is something like what if scenario. For an example, if you have a single cylinder engine, and what you want to do is you want to bore it out. So say you have a 5.8 liter engine, you want to bore the cylinder, you want to make it 6.5 liter engine, and then you want to add a turbo. What would happen to engine performance? What would be the temperatures? What would be the pressures? Those questions are super duper important, just to make sure that the engine can deliver the power and engine can sustain those higher pressures, higher temperatures, and higher loads. So if you want to design a turbocharged engine, or if you want to design a supercharged engine, that option is also available. So this software is very capable. Now, as you know, MATLAB we use a lot. Now, if you want to interface Lotus engine simulation with MATLAB Simulink, you have a data pipe that you can actually use, so that the Lotus engine simulation software can exchange and interact with MATLAB simulation environment. And MATLAB, so where does it go? So for an example, the loads and the stresses that you get from Lotus engine simulation software can be transferred to MATLAB for dynamic analysis or some other analysis, or maybe you can use sim mechanics for vibration analysis. So this software is quite capable, and I will give you a basic overview of the software, but this software is very intuitive and easy to learn. So my strong recommendation to you would be, even though it's not part of the regular curriculum, in a sense, like I'm not going to ask you any quizzes, questions, or I'm not going to give you any exams. For your own understanding, please try to do these tutorials. So I presume at this time, most of you are downloading the software. If you download the software, please install the software, and I will actually quickly walk you through what it is. So Lotus engine simulation is a comprehensive engine simulation software, and that is actually validated. So the Lotus cars, this software originated at Lotus cars, and you can go and visit Lotus car website. They build fantastic European cars, exotic high performance cars. And then if you go down, there are 4 steps. So basically you generate the model, apply the load boundary conditions, run the simulation solver, and we view the results. This is the setup wizard, and I will walk you through this setup wizard. Then these are all the tutorials. There is a fantastic help file, and I just want to tell you that just go through this help, because this will actually give you the practical knowledge about engine design. This is sort of a no nonsense condensed textbook. It will say, if you want to do combustion, there are 3 types of combustion models. These are predominantly used without going into the theory and details of it. If you have engine configuration like this is the preferred combustion model. If you have engine configuration like this is the preferred combustion model. So this kind of gives you a condensed information from the text. And that's actually very good. I have gone through this help file. It will talk about the program overview. It will talk about, and this is something that we will do today quickly. So what you do is, it is something similar to a very graphical, intuitive user interface. So once you start, you will have a blank canvas. And this blank canvas is basically where you grab the blocks from the library, drop the blocks onto the canvas, make appropriate connections, and then add the parameter values. So as you can see, so what you do is you add the cylinder block. Then here you can actually enter the cylinder dimensions. So what do we want to do? In today's class, what I'm going to do is I'm going to work out a problem on engine design, wherein we would be given power and the requirements. And the first thing what we are going to do is we are going to find the bore and the stroke. So once we find that bore and stroke information or piston to bore ratio, what you do is you basically go ahead and then basically add that information over here. So you would enter the bore, you'll enter the stroke. It actually asks you whether you add a liner or you don't add a liner. That is up to you. It's totally fine. So those details we can work out. Then again, this is something that we are not going to talk from mechanical design aspect, but this is super important that whenever you are going to do the engine design, there is something called as the Anode Model, there is a Voskhod model, and there is Axial model. These three models are the standard, very fundamental heat transfer models for engine. Each model has its own advantages, disadvantages, and the region of operation. So you can actually look through the information and then you have to select an appropriate heat transfer model. In our textbook, this information is not given, but I'll tell you what has done. In our textbook, a very simple formulation is given that gives you the temperature heat transfer coefficient. So that is just for hand calculations, but for actual calculations, you will have to select an appropriate model. Then if you go down, what you do is you want to add an intake valve. So you would add an intake valve and then you have to specify the properties of the intake valve. And this is something super important which I want to talk about. This is called as the valve timing diagram. At this point, I want to ask you this simple question. How many strokes do we have? So how many cycles do we have in a power cycle? I mean, in an internal combustion engine? Suction, compression, expansion, and exhaust. Everybody agrees? What's going to happen during the suction cycle, suction part of the cycle? Exhaust valve is closed, inlet valve is open. Do you agree with me? So what it means, and this is very important, from theoretical point of view, when the crankshaft is at 0 degrees, intake valve should open, and when the crankshaft is at 180 degrees, intake valve should close. Do you agree with me? Because during suction, the intake valve should open, and at the end of the suction, intake valve should close. Suction is 0 to 180 degrees. But unfortunately, in practical situation, it doesn't work that way. The reason for that is the valves, all the mechanisms have their inertia. So you need to start opening the valve slightly before 0 degrees, and you have to close the valve after 180 degrees. So actual wall timing diagram is different than the theoretical wall timing diagram, and that affects the performance of engine. So that is what this is talking about. This is TDC, which is 0 degrees of crankshaft. This is BDC, which is 180 degrees of crankshaft. Intake valve is going to open 15 degrees before, and it's going to close 60 degrees after. You agree with me? Now there are issues with this. Let's understand what is happening. So this is where the suction is occurring. So this is where TDC to BDC, the charge is sucked. The next part from BDC to TDC is charge being compressed. But recognize, as the compression stroke is starting, the intake valve is still open, which means some teeny tiny part of the charge would escape from intake valve. And if you have charge escaping, that means your efficiency is going to go down. You don't want charge to escape. So you have to adjust this very critically so that you have the charge, you can compress it, and you get the maximum efficiency and power from that engine. So that's why IVTech engines, since the engine running at slow speed has different valve inertias, the engine running at higher speeds have different valve inertias. That's why you have different PDC, the valve opening and valve closing timings, just to make sure that those inertia effects are taken into consideration. That is what they call as IVTech technology. So then what you do is you go down, and then what you add to it is the exhaust valve. So again, same issue with the exhaust valve. Exhaust valve should open at the beginning of the exhaust stroke and should close at the end of the exhaust stroke. But because of the finite inertia of the components, those in exhaust valve should open before the exhaust stroke starts and should close after the exhaust stroke has finished. You agree with me? But that's again another different problem. What is the problem? Then you have an overlap. What it means is you have a small region wherein the intake valve is also open and exhaust valve is also open. So do you see what's going to happen? Yeah, basically the charge, the fresh charge would get contaminated, which would affect the efficiency. There are ways for doing that. Basically, you design the valves and you design the combustion chamber. That is where those hemispherical combustion chamber and all that, those things come in the picture. Because what you do is you direct the flow in such a way that that contamination is minimized. And the exhaust charge is actually propelled out from the from the intake charge. So basically intake charge comes in and it sweeps the exhaust charge, and by the time it's actually finishes sweeping that out, the exhaust valve gets closed. So all these small details are super important, and you need to have some practical experience. But then valve opening and closing profiles also play an important. Do you want bang type of opening, like valve open, close, or you want gradual opening? If you want gradual opening, do you want opening to be slow or fast initially? And then how do you want it to close? Do you want it to close like this, or do you want to close it like smoothly? And remember, all these things are happening very fast. So you need to know how should be, and then you have to map it to the cylinder phases, because you need to know exactly where the piston is when the valve is opened and closed. Because please try to understand, fluid will flow from higher pressure to lower pressure. So what it means is, if you want to control the flow direction, you need to have that pressure differential, and that totally depends upon where the piston is. Everyone understood this? So you will have to do this mapping. There's a lot, and I took about 3 to 4 courses on internal combustion engine. So there is a lot to talk about. And then again, you have these flow coefficients, and then that you can actually decide what type of ports you use. And then what you do is, if you go down, you will have these different flow coefficients, and for different geometries of the pipes, geometries of the valve, geometries of the valve openings, you have these flow coefficients. Then what you do is you have plenum, intake plenum, where air fuel gets mixed. Earlier, we used to have carburetor, wherein the fuel would come, the air would come and the fuel would get atomized, just like our misting system that we see, the fuel will get atomized and that air fuel mixture will get fed into cylinder. Nowadays, what we have is we have fuel injection. So basically air comes in and the fuel spray is injected into the airstream. And then what you have is you have the gas pedal that controls the butterfly valve, which is the amount of air fuel mixture that is entering the cylinder. So if you go down, you can decide whether the system is port injection, what type of fuel you are using, all that stuff. And then what you want to do is engine. So whether you are designing a small engine or a big engine, you should have a decent idea in what RPMs you want your engine to operate. So you provide those RPMs, you add additional information like what is the ambient air, ambient temperature, intake pressure. So basically intake pressure of 1 bar, which means it's not turbocharged. You are not compressing the air and putting it inside the cylinder. Then all that stuff you enter, and then you need to add the different test conditions, because what you want to do is, so engine performance is different at different speeds. And as an engineer, you need to know, like, if the engine is revved or if engine slows down, what is the effect on power? What is the effect on torque? What is the effect on efficiency? So you need to generate what is the effect on fuel consumption. So for that, you need to create the load cases at different speeds. You can look at the steady state operation. You can look at the transient operation and then run the engine simulation. And at the end, what you do is you'll get the results, and then those results can either be saved in a file or in a database. That database can be actually accessed for viewing, and then you can visualize the results. And it will actually tell you that how the engine performed. It will also kind of give you these results in some type of text format, and then it will generate these plots. These are the common plots that are used. So what happens now? So these are the plots which are generated from the engine simulation. What you do is you take that engine, put it on a dyno, and then run the test and see how good your results are. For an example, if you look at this plot, red line is indicating the power. So it shows at 1000 RPM, the power generated is about 5 kilowatt. At 7500 RPM, the power generated is about 25 kilowatt. But here is the problem. If you look at the torque is dropping down. So which means even though you are having more power, the torque has dropped, which means you cannot actually have this engine supporting a high torque load. Like you can't put this in a car and have that car go uphill. Then look at this Bsfc. Bsfc is the brake specific fuel consumption. So this actually talks about how efficient the engine is. Bsfc needs to be as low as possible for engine operation. So as you can see, initially the Bsfc is low. brake specific fuel consumption is low, gradually at higher RPM, the brake specific fuel consumption goes up. Then another important question is, what is the pressure inside the cylinder? Because the mechanical parts of the engine are designed for certain stress and strains. If the pressure inside the cylinder or temperature inside the cylinder exceeds those mechanical limits, the engine is not going to perform. So as you can see, this is called brake mean effective pressure, BMEP. This is the pressure inside the cylinder when the engine gets a run from 1000 to 7000 RPM. So you want to kind of see, you want to operate in a certain region. So for an example, if I were to see here, I can reasonably say that engine is going to redline beyond 5000 RPM. So that is how I would decide this would be the red line. That doesn't mean that engine won't be able to operate all the way up to 7000 RPM, but as a designer, you will not recommend engine to be operating in this region. So that's why you have that red line on your internal combustion or cars. And that is where the engine is going to start making those strange sounds. Everyone understood this? Then another important part is, we talked about, you can actually go through the, So this is the first tutorial and I went through the detail because I'm going to run this tutorial, a simple test case using on the software, but I would strongly recommend that please go through these actual engine designs. They are very useful and you will learn a lot more than what you have seen reading the book by running the simulations and doing these tutorials, because this is how the practical engine design is done. The textbook method that we are using is just to give us some preliminary dimensions of engine. This is the bore, this is the stroke, this is typically the crankcase diameter, this is the type of piston we are going to use, this is basically the size of the connecting rod, this would be the section of the connecting rod. But if you want to get into the detailed design, manufacturing, production, you will have to resort to the design simulation softwares. Everyone understood this? But the exercise that we do is very important because that gives you a starting point. Right now, you don't know 25 kilowatts, 3000 RPM engine. Should I use 80 millimeter bore, 100 millimeter bore? What would be the cylinder dimension? Our hand calculations, they give us the starting point. And then these computer simulations help us refine those dimensions. Same thing we did with the finite element analysis. So initially we came up with some basic dimensions. Then we used that to construct the CAD models. And then we did a detailed finite element analysis to make sure that the design would be able to support the loads and the stresses. Everyone understood this? Okay. Online students, any question? Now what I'm going to do is, and if you are with me, I would strongly recommend that you do this exercise with me. I have already installed the Lotus engine simulation software. Online students, can you see my screen? I hope you are able to see my screen. And at this point, I'm going to recommend that you open this Lotus engine simulation software. Now, here you have a lot of options. What I'm going to do is, you can start with a blank file. You can start with the concept tool. You can start with the friction estimator tool. You can start with the port flow analysis. You can do with combustion analysis. But I'm going to just work out a very simple problem. So I would start with engine simulation. And I have already created a file. So what I want you to do is, if you are with me, I'm going to walk you through this process and please follow my lead. First, grab this cylinder on the left-hand side and put it in the canvas. Drag and drop. Double click. It will actually tell you the dimensions of the cylinder. So it will tell you bore, stroke. So, and how is it related to the design that we are going to do next? Later today, we are going to start with engine design. And the problem will be design a cylinder piston for an engine. We'll start with cylinder design. Design a cylinder for engine with 25 kilowatt running at 3000 RPM. We'll perform our calculations and get the value of bore and we'll get the value of stroke. So that is the information that you would enter. Then clearly the next question is, are you using the diesel engine or a gasoline engine? Gasoline engine would have low compression ratio, typically between 9.5 to 10.5. The diesel engines would have higher compression ratio, 19 to 21. So since we are going to use the gasoline, we are going to use the compression ratio for the gasoline. So if you look at con rod length, that is something when we will decide when we actually design the connecting rod, that information needs to go in the con rod connecting rod length in millimeter. Everyone understood this? So that is the information that it needs. Then you have some additional information. And clearly at this point, again, it's going to be an iterative process. So if you have you seen the inline cylinders and the V cylinders? So basically, if you have a cylinder that is vertical, it will also talk about what is the cylinder axis angle. It will talk about what is the piston mass, what will piston mass, pin mass, con rod inertia, all that type of stuff that you can do. Then you want to decide what type of mechanism is converting the reciprocating motion into the rotary motion. And I tell you why this is important. About 10 years ago, I worked on a research project where we came up with this idea where the piston and the connecting rod are made up with one solid piece. So there is no articulation. So we used a hypocycloid gear mechanism that would take the translational motion of the piston and convert that into rotary motion. And the kinematics of that mechanism is completely different than the slider crank. So what you want to do is you have an option of changing this mechanism. So you can actually create a user subroutine. So look it up. People have talked about YC engine. It has a different profile. There is a hypocycloid engine. It has a different profile. But this is basically the standard slider crank mechanism that we are going to do. And this software is so nice that it's going to give you some hints as you proceed. So since we are working on the cylinder, we need to have something before the cylinder and we need to have something after the cylinder. So the components before the cylinder are called upstream components. And these are the allowable upstream components. So for an example, this is valve, I think the turbocharger and all that type of stuff. So these are allowable upstream elements. And then these are the links that would link these different components. And these are the allowable downstream components which are after cylinder. So you can actually drag and drop. But assuming cylinder, any question about the cylinder design? Then what you do is you go to the intake component. On this intake component side, what you have is, I just use a simple valve. So what you do is you go here and drag and drop this valve over here. And then once you go onto the valve, it actually will tell you that this is the default intake valve. It has valve opening, valve closing, very important. Can you see that the valve is opening 10 degrees before and valve is closing 66 degrees after? Then that valve needs to lift up so that the valve, that cavity can open. So it is telling you how much should be the lift. So the max lift of the valve is 8.5. Then it is going to ask you whether you want that valve to lift quickly or do you want that valve to lift slowly. And that is where this lift polynomial comes in the picture. So basically, if you click here, there are different lift polynomial. You can choose different polynomial curves and then actually play with it. Okay, I would strongly recommend that as you do, I would encourage you to go work through the simulations with me. And then I think this is it. Yeah. And then you have this opening lash, closing lash, event display, timing display, all that you can turn on, turn off. The next thing is you can't just have a valve, you need to have a port. And the port is where the charge would flow through to the valve. And then for that, the most important dimension is what would be the diameter of the port. And then again, I don't know, if you go to Walmart or any tire or any, they say that we will clean your engine ports with, I'll add some additives and that is supposed to clean the carbon on the valve ports and all. So initially the valves are super clean. Then after some time, what happens is the valves get coated with carbon. So basically the valve's property change. So what you can do is you can actually decide whether your valve is a good valve or a poor valve. And then that will affect the performance of the engine. So I'm just gonna say good valve. And then this is the boundary. This boundary talks about what type of intake it is. And then as you can see, this is the intake at the fixed pressure from the atmosphere. But if you add a turbo or so for example, look here. So this is, you can add so this is actually basically there is something I want to talk about. This is not used in practice. There is a concept which is called as the rotary wall. Instead of the valves that go up and down, what you have is you have the valves that rotate and they open and close. So this is the rotary valve. They're not used commonly, but I have played with those. Then this is so what I would do is please go through all these parts, drag and drop, and then it will tell you a little bit more information about it. And then you can actually look at the help file. This is very useful. Then you can go on to the exhaust side. So on the exhaust side, you have this exhaust valve. And this exhaust valve would also have open, close, all that type of stuff. Same information as the intake valve. You would have a plenum exhaust port and then you will have the fixed default exhaust. And once that is done, you can go to this gas tank symbol that talks about what type of fuel we are using. So in this particular case, you are using gasoline, and then you can have an option whether you are doing carbureted or whether you are doing port injected. By the way, port injected engines are more efficient, carbureted engines are less efficient. So, but you can actually have here, you can have a carbureted engine, you can have a port injection engine. Direct injection and indirect injection, they are used in diesel engines. So in diesel engines, as you know, what happens is the only air comes in, air is compressed at a high compression ratio, the temperature is very high, pressure is very high. At that time, we are injecting the diesel fuel, fine, very fine atomized spray of the diesel fuel. There are two ways to inject. Either we can inject the diesel fuel coming directly into the coming air stream, or we can inject a diesel fuel onto the combustion chamber. So that's what it means, direct injection or indirect injection. So if you are injecting directly onto the incoming charge, incoming air, then it's direct injection. If you are injecting it on the the combustion chamber, that becomes indirect injection. So there are a lot of options here, and once that is done, what you do is basically you go to tools, and then you do data check, and then it will show you that if all the components are appropriately defined, then what you want to do is you want to do so. So let me see. There is one more thing that I want to talk about. So to builder interface, simulation parameter, results graph, results view, simulation concept tool, friction estimator. Okay. And let me see, tools, results, solve, view. And at this point, you can actually, so you can design an MRS file. So R1, R2, and then it will run, and then you can see the results. So we actually did not define the steady state, so you will actually get all these values. So you will get the result. You will also be able to see the results graphically and all that type of stuff. So please run this, play with it, and then you will see this is actually a good software. So any questions about the operations? And just with any software, more you play with it, the better you will get at it. Now what I'm going to do is I'm going to stop share, and then I'm going to discuss the cylinder design. So any questions from anyone?
popular? Most, because you said different companies will use different software. Is there one that's more popular?
It completely depends. There is another software that I have personally used, which is called Ricardo Engine Simulation. That's a very famous software. Then there is Fluent. Then ANSYS sometimes is used for some parts of it. And these companies like GM, Ford, Chrysler, they have their built-in software tools. Because if you think about it, they have been designing and developing engine for last hundreds of years. So they have a lot of legacy data, legacy tool, legacy codes that are used for designing. But the good news about Lotus engine simulation software that it is available free of cost to the students and researchers, because some of these engine simulation softwares are very, very expensive and we will not have access to it. I mean, and their licenses, they go in thousands. So, I mean, but if you go to say Ford or General Motors and then say, hey, I've done engine design simulation using Lotus simulation software, I'm sure they will be super impressed. Okay. Okay. So in last class, I gave you kind of an outline for engine design. Now we actually looked at the cylinder design. So let me work out a very quick problem on the design of a cylinder. So this problem is design a 4-stroke diesel engine the brake horsepower is 5 kilowatts. The speed is 1200 RPM. The indicated mean effective pressure is 0.35 Newton per millimeter square. Efficiency mechanical is 80%. And for this engine, we have to first find out what is the diameter, what is the stroke length, what is the thickness, and size of bolts. So let's quickly recap. Indicated power is IP. This is the power generated in cylinder. Then there are friction losses. And what you have is you have the brake power. So you have indicated power, and you have the brake power. Indicated power is greater than brake power. Efficiency mechanical is equal to brake power divided by indicated power. So brake power is 5 kilowatts. So from here, you should be able to find out the indicated power. Indicated power is 6.25 kilowatts. Now at this point, we have to decide what type of engine configuration it's going to look like. So essentially, we need to find out L to D ratio. So L to D ratio, and I'm going to assume it to be 1.5. What that means is stroke length is equal to 1.5 times diameter and then indicated power is equal to P times A times L. Now this is the 4-stroke engine, so please note this is N by 2 divided by 60, and this is because with the 4. So 6.25 0.35 pi by 4 T square L times 1200, and you can, as you know, L by D ratio is 1.5. This equation can be substituted here, and the entire equation will be in terms of D. Once you solve, so these are the answers. So you get diameter as 115 and you get the stroke length at 172. So next part, we have to find out the head thickness. Head thickness is T. For that, we need to find out P max. P max is 6 to 10 times. P max is the maximum pressure inside the cylinder. 6 to 10 times indicated mean effective pressure. I'm going to assume it to be 7. And I'm going to assume sigma is equal to 42 Newton per millimeter square. And the thickness, if you look at the equation that I gave you in last class, C P max divided by sigma. 115, 0.1, 2.1, 42. So the thickness as 9 millimeter. Next part, and I will use this side, is we need to determine the bolt size. So force is equal to pi by 4 d square times P max. This is the maximum force that is going to be on cylinder head. So if you look at the cylinder, head, the bolts are going to be here, and the maximum force here is pressure multiplied by area. So this equation, pi by 4 2.1 is 21.8 kilonewton. Now I'm going to assume number of bolts. And I'm going to assume 6. So force is equal to pi by 4 dB multiplied by number of bolts multiplied by sigma t. Is 21.8 10 to the power 3 pi by 4 dB square 6 multiplied by 60. And you can solve this equation, and that will give you the diameter of bolts.
The number of bolts just assumed based on the size, like the table that's for us.
So if you look at the diameter is 115. Now it's not an easy question to answer. I'll tell you what happens. Let me show you. This is the cylinder. And then this is the cylinder head. If you look at the top view, the bolts have two purposes. The first purpose is to ensure that the cylinder head stays attached to the cylinder. Also, the other purpose is that this joint is leak proof. Now we need to make sure. So for an example, there is going to be a liner here. There is going to be a liner. So this is liner, and you're going to have bolts. So bolts would make sure the structural integrity and also it would make sure that its joint is leak proof. So for structural integrity, the number of bolts may be less. But if you want to ensure that joint is leak proof, then you want to add more number of bolts. But you can't just on your own go and start adding as many bolts as you can. because here is the practical problem. Imagine that this is the cylinder. You have a bolt here, you have a bolt here, you have a bolt here, you have a bolt here. This bolt is compressing the gasket which is between the cylinder and the head. That is called as the liner or the gasket. If you start drilling another hole over here, if you start drilling another hole here, if you start drilling another hole over here, if you start drilling another hole over here, what's going to happen is there will be a region here where even though you don't anticipate, there will be a region of deformation. And that deformation, rather than sealing the joint, would give you a weak section where the gases can escape. So that's why what you want to do is, and there are design guidelines based on the pressures, based on the diameters, based on the applications. For example, in the diesel engines, the bolt design guidelines or number of bolts are different for different cylinder diameter. For gasoline engine is different. It also depends upon what type of liner is used, because usually we don't use we use a metallic liner. So we want to make sure that under that pressure, that metallic liner should not develop any micro cracks. So the number of bolts, the sizes, the location, that all depends upon how that engine is configured. So typically, once you go, there would be a data book, and you will see, okay, and that data book comes from, because for the last 100 years, engineers played with different bolt dimensions, different gasket materials, did some experiments, and came up with some design thumb rules that are like empirical formula that you can use for bolt design. And design of leak-proof joint itself is an important concept, because the way the leak-proof joint is assured is using the stiffness of the parts that are coming in contact. So there is actually a chapter in your textbook that talks about design of bolted joints for leak-proof assembly. So if you design a pressure vessel, it's a different type of design. Internal combustion engine, it's a different design, and so on. So I'm going to stop here. Okay, so now we will proceed to another important part of the engine. We looked at the cylinder design. So the next part is design of piston. So usually the piston is cast aluminum, and it looks something like this. And please understand, the piston is subjected to extremely high heat on one side. So what you want to do is you want to design the piston in such a way that the heat on one side gets quickly dissipated. The other problem is the piston is also a component that is reciprocating at very high velocities. So there will be very high inertial forces on piston. So you want to make sure that the piston is able to sustain those high inertial forces. So let's talk about the piston nomenclature. So this is called as the piston crown. These are the grooves for piston ring. This is the groove for oil ring. And this is where the piston pin sits. And what you do is you insert the piston pin and you add a circlip. So this is the circlip groove. This is called as the top land. This is called as the ring area. So ring. This is called as the skirt. This is the total length of the piston. This is the thickness of the piston. If you look at the piston rings, they are something like this. They are not a complete ring, but they are like rings like these. And it's very interesting, those piston rings are assembled. They are slightly oversized. So what they do is, first the piston rings are placed inside the piston. Then there is a compression tool that actually compresses the piston, and then the piston is kind of dropped down in the cylinder. So this whole thing is called as piston barrel. And piston needs to be extremely lightweight. So, and it needs to be able to dissipate the heat very quickly. This is actually called as the top thickness, TH. And you have, this is where the piston pin gets placed. So this is piston pin. This is called as the thickness of the rib, PR. So this piston is hollow, but inside the piston, again, the stresses or the loads that are coming on piston are very high. So that piston needs to be reinforced, and that's why you have this ribbing to reinforce the piston. So how do we design the piston head? So once again, just before we start, I just want to tell you that these top rings are for sealing, and this bottom ring is called as the oil ring. This is for scraping. So too much oil is also bad because that reduces the combustion efficiency, that increases the pollution. So as the piston is going up and down, you want to scrape the excessive oil at the interface. So how do we design piston head? And there is something called as the Grashof formula. And this Grashof formula is pH 3 PD square 16 sigma T. This is based on the strength. So please understand there are two important considerations for piston design. So for piston design, one aspect is strength and second aspect is heat dissipation. So you have strength and you have heat dissipation. So in this equation, P is the max pressure, D is the diameter, sigma T is the tensile strength. So which is 35 to 40 Newton per millimeter square for cast iron, 50 to 90 Newton per millimeter square for aluminum, 60 to 90 Newton per millimeter square for steel. So this formula is based on the strength. There is another formula which is pH that depends upon H divided by 12.56 K TC minus TE. Now, when we were going through the Lotus engine simulation software, we were looking at the heat dissipation inside the cylinder, the cylinder. As you can see, there were 3 combustion and heat transfer models that we looked at it. But the textbook just provides one formula, which is one empirical formula where H is the heat flow through piston, K is conductivity factor, and that is 40 watts per meter degree Celsius for cast iron, 52 watts per meter degree Celsius for steel, and 175 watts per meter degree Celsius for aluminum. Now, the thing here is, if you have this heat that is generated in combustion, you really don't want the 100% of the heat to flow through the piston thickness. So we assume certain percentage of heat that flows through the piston and certain percentage of heat gets dissipated from the piston skirt. So Tc is the temperature at piston center Te is temperature at piston edge. And typically Tc minus Te is approximately 220 for cast iron and 75 for aluminum. So how do you find out the value of H? So value of H is a factor C multiplied by a higher calorific value of the fuel multiplied by the mass flow rate multiplied by the brake power. So M is brake specific fuel consumption Bp the brake power HCV is a higher calorific value and typically for gasoline 45 10 to the power 3 kilojoules per kg gas C 0.05. Next part is design of piston ring. And if you say T1, the radial thickness of the ring, then T1 is equal to diameter 3 times PW sigma T. If you look at the piston ring is going to look like this. This is T1. Actually, and then this is the axial. So D is a cylinder dia. Sigma T the tensile stress. (85 Newton per millimeter square). PW is the gas pressure on cylinder wall. On cylinder wall, it's typically 0.025, 0.04 Newton per millimeter square. This is T2. So next part is the axial thickness or the side thickness. Where NR is the number of rings. Width of the top land. Which is P1. TH 2.2 times TH. B2 is the width of the ringland. Next part is design of piston barrel. Maximum thickness. Next thing is design of piston skirt. And F side load is, if you think about the piston and cylinder, so this is the cylinder and there is this piston. So as the piston is going up and down, because of the articulation of the connecting rod, you are gonna get side load. So you are gonna get side loads. So side loads. And that side load is assumed to be 0.1 times the total load that is coming on here. If F is the total load, 0.1 times F is the side load. and that is PB, which is the bearing pressure, D times L. So bearing pressure is a design parameter. D, we know we already calculated, which is the diameter, and that should give us the length of the skirt. So skirt means the bottom part. As you can see, this is skirt. This guy. This is skirt. The next part is design of piston pin. Piston pin would look something like this. This is the length of the piston. So if you look at the piston pin, the piston is here. This is where the pin sits. So this is the pin. And then here, there will be a connecting rod, small end. And then there will be circlip grooves here. So the way we solve this problem is maximum bending moment is approximated to P times D divided by 8, which is the max. P is equal to gas load pi by 4 D square. E is the pressure, max pressure, and sigma B is equal to M max divided by I multiplied by dO by 2. And typically DI is equal to 0.6 times DO. And I is pi by 64 d outside to the power 4 inside the power 4. Any questions about the piston design? Any questions? Online students, any questions? Yeah.
So, among the diesel and petrol piston heads are different. So, does the calculation change?
Slightly. So basically, if you look at the diesel pistons, they are stronger. And the heat dissipation equation for the diesel pistons is really different. But if you look at the textbook, they are just using one single equation for the piston design. But what usually we should do is we should follow these calculations, get some rough numbers, and then use the software like Lotus engine simulation to refine the design. As a matter of fact, there are softwares that would actually help you design just the piston, design the shape of the piston. I don't know if Lotus has released that software. I know they have it, but I don't know if it is available for students to use. Then you can actually manipulate the piston geometry, decide the distances between the piston ring, oil ring. All these parameters are very important. And you won't realize that it's so precisely engineered. That's why you are achieving the maximum efficiency possible from that internal combustion engine. Otherwise, if you look at the overall concept, it's such an abstract concept. Like you have this gasoline, a fuel that you are burning and you are extracting mechanical power from it. But you need to do it within the boundaries of thermodynamics. You have to do it within the boundaries of the materials can do and still extract every single thing or every single amount of power from that drop of fuel. So that's why over the last hundreds of years, people have spent billions, probably trillions of dollars in perfecting the internal combustion engines. So I get asked this question. So what do you think about the internal combustion engine with this electric cars? Is it going to go away? My honest answer to that is I don't think internal combustion engines are going to go away for next 50 years. For multiple reasons. The first and foremost, that there is so much legacy of supplier chain, inventory, and parts that is set up for internal combustion engine design, that internal combustion engines will continue to come to the market. There is new engine development still going on. So for example, with these Teslas and the other car manufacturers coming up with, and governments providing so much incentive to electric cars, still the automotive companies are investing heavily in new and different types of engines. So then the next question comes is, where does the power come from to generate the electricity? At the end of the day, significant amount of that power comes from fossil fuels. And how do you think fossil fuels they converted into electrical power? By means of combustion, whether it's an internal combustion, whether that's an external combustion. So in my personal opinion, engine design is not going to go away. What you will see is you will see more and more efficient engines. You will see more and more hybrid engines, and you will see some application of electric vehicles or of electricity in certain targeted areas. But for the whole electrification to occur, we are way behind. So that's why somebody asked me when I was teaching this,
So I think internal combustion engines will go away. Why are we studying internal combustion engine? I said, no, I mean, if that is the case, Honda, Mitsubishi, Toyota, Ford, Chrysler won't be investing billions of dollars in developing engine technologies, the engine facilities. If you look at the new Mercedes vehicles, they give you the big luxury SUV. It gives 40 miles per gallon. Why? Because they have introduced the hybrid propulsion power plants in there. See, we want comfort, we want luxury, but we don't compromise on speed. We don't compromise on efficiency. So how, and then again, we need access to fuel everywhere you go. I mean, charging stations are fine, but they are not everywhere. You can't go into a remote area and expect to find a charging station. So fossil fuels, at least I believe till my lifetime, internal combustion engines are not going to go away. You will see cars, you will see improvement in the cars. I strongly believe that there will be hybrid technology that will be used in the cars to improve the efficiency of internal combustion engines, but purely electric cars will not be a viable solution for next 50 to 60 years. It's just not possible, because where is the electricity coming from? We are not generating electricity from solar. We are generating electricity from power plants. How are power plants generating the electricity? By burning fossil fuels. What type of engines are they using? They are using turbines, which is external combustion engine. Sometimes they use internal combustion engines. Sometimes they use some combination. Sometimes they use hydropower, but hydropower is very small portion of the power that is generated in the United States. Natural gas is very important in that region, in that area. So I personally think understanding and learning internal combustion engine design is very important. So don't think that it's going to go away for next at least 50, 60 years. Okay. Okay, let me work out a problem, and I will solve this piston design problem, and then we will stop. So piston design. Design a cast iron piston for following. The bore is 100 millimeter. Stroke is 125 millimeter. P max 5 Newton per millimeter square. Indicated mean effective pressure 0.75 Newton per millimeter square. Efficiency mechanical 80%. Brake specific fuel consumption is 0.15 kg per horsepower, brake power per hour. Higher calorific value is 42 10 to the power 3 kilojoules per kg. Speed 2000 RPM. So step 1, piston head design based on strength. TH. I'm using sigma T. Four-stroke engine. Zero point 0.75. .27 kilowatts. Brake power. Efficiency mechanical times indicated power is 9.81 kilowatts. Fuel consumption per hour we have to find out H, which is 0.05. I calorific value times fuel consumption. So this comes around 850 watts, kilojoules per kg. Then from heat dissipation, TH is equal to H 12.56 times K times TC minus T. And K for cast iron, please look at the textbook. It's 46.6 for cast iron. And TC minus TE, $220. So substitute value here, substitute 46.6, substitute 850 here, and TH should get about 16 millimeter. Compare that with the previous answer. So we got TH as 16, so we are okay. So we'll say TH equal to 16 millimeter. Next part is piston rings. assuming 4 rings, T1 sigma T is equal to 90. So T is equal to 4 millimeter. T2 is T 10 times an R 100 divided by 10 times 4, 2.5 millimeter. So power and number of rings. This is something to keep in mind. The power is less than 12 kilowatts, 4 rings. If it is between 12 and 20, typically 6 rings. Is greater than 20, anywhere between 6 to 8. This comes from the textbook. So textbook. Barrel equal to B T plus 0.4. So you get about 3.4 plus 4, so about 4 millimeter. Next part is design of piston skirt. Side thrust F is equal to mu times pi by 4 times P. Mu I'm going to assume 0.1. Mu is the coefficient of friction between the cylinder and the piston. 100 square, 5, 3, 9, 2, 6 newtons. And side thrust is equal to sigma B times T times L. Sigma B is 0.45 times T is 100 times L, and we equate this over here. That gives me the value of L is equal to 90 millimeters. The total length L is equal to 90 plus 4 times 4 plus 3 times 3. This is for the rings, which comes about 130 millimeter. And it might be a good idea to draw a neat sketch of the piston. So the next part is design of piston pin, last part. So total force pi by 4 times d square times p, pi by 4, 100 square times 5, 39 kilonewton. Bending moment maximum F times L divided by 8, so which is 39 10 to the power 3. L is the same as the diameter, 100 divided by 8. And this Bm max has to be equated to sigma B m divided by I multiplied by Y. I'm assuming sigma B 60 Newton per millimeter square. 60 bending moment comes around 480 10 to the power 3 pi by 4. D inside is 0.6 times D outside. And from once you solve this, you'll get the value of D, and that would be the diameter of the pin. And there are some other dimensions, but those are based on the empirical dimensions, so and empirical guidelines. But this is how we can design the piston. So I'm going to quickly go through the process. So we have to design a cast iron piston. In this particular case, the data is given. If this data is not given, this information comes from the cylinder design. So if you look at the first part where we designed the cylinder, we decided the bore and the stroke that comes from the cylinder design. Pmax also comes from the cylinder design. IMEP, efficiency, all this information comes from the cylinder design. So think about it like you are given design specs, you design the cylinder, got the bore and stroke of the cylinder, and you are using that to design the piston. First, step 1, you have to find out the piston head based on the strength using the equations. Second part, finding out the piston head thickness using the thermal criteria. Then next part is you have to decide the piston rings. And the piston rings would have two thicknesses. One is axial thickness and the radial thickness. So we find axial thickness, we find radial thickness. Next step is we find the piston skirt length, and that comes from the side load and the bearing stress. And then the last but not least is we design the piston pin. And afterwards, we can draw a neat sketch of the piston, something like this, and then show all the dimensions of the piston. So with that, I'm going to stop here. The only two important parts that are remaining is connecting rod design and the crankshaft design. So what I would do is I would go through connecting rod design, crankshaft design process, work out some problems in next class. And there are some last little bit of design of valves, springs, and then the valve trains that I will talk about later in the course. So with that, I'm going to stop here.